Mm. Bom dia, boa tarde, boa noite a todos. É uma grande honra estarmos aqui hoje. Meu nome é Júlia Leonardo, eu sou estudante da Universidade Federal de São Carlos e sou aluna do professor Tiago Souza. E hoje eu estou aqui para anunciar a nossa palestra hoje, que é Dynamic Pile Testing, Basic Principles that Interpreted and Effective Application. Como o nome já sugere, a nossa live hoje vai ser em inglês. Então, agora eu vou mudar o idioma, então eu vou fazer as apresentações novamente, agora em inglês. Good morning, good afternoon, and good night for whatever you are watching us. It's an honor for me and Geotecnia Brazil receive Mohamed Hussein. My name is Ana Julia Leonardo. I am a student of Federal University of São Carlos, and Dr. Thiago Souza is my professor. Today we are here to other amazing presentation. It's called Dynamic Pile Testing, Basic Principles that Interpretations and Effective Applications with Dr. Mohamed Hussein. I will read the CV for Mohamed Hussein right now, and after this, I will give the talk to Mohamed so you can enjoy everything he have to show for us. Mohamed Hussein, PR, Life Member ARCA, is the Principal Engineer and Executive Vice President of GRL Engineers, as well as the Executive Director of Global Industry Related at Biodynamic, the oldest and largest company specific and deep foundation test service and equipment manufacturing, respectively. With a career span of 14 years, Mr. Husaf was consulted on more than 1,000 deep foundations projects around 25 US states and several other countries. He is a frequent organized and instructor of education courses and seminars on deep foundations, including the American Society of Civil Engineer. Continuing education class, Deep Foundation, Design, Construction, and Quality Control. He is an active member of Deep Foundation Relative Technical Committee at DFAI, ASTM, PDCA, and ASCA. He served as chair of the ACCA Geo Institute Deep Foundation Committee and PDCA Education Committee, and he currently chairs the PDCA Technical Committee. Mr. Joseph was recent numbers professions and industries awards and honor. He was a author over 30 technical papers and co-edited 10 engineer books. He holds a spectral level certification and dynamic massive and analysis professional test and the foundation QR high straight dynamic pi testing examination. And he is a licensed professional engineer in multiple US states. He also convened and shared the first International Foundation Congress Equipment Expo, which has since become a landmark record and event in the industry. It's an honor for us having you here, Mohammed, Professor Mohammed. And now the talking is all yours.
Thank you. Thank you for the kind introduction. And hello, everybody. Thank you for tuning in to this presentation on dynamic pile testing, basic principles, data interpretation, and effective applications. As had been introduced, my name is Mohammed Hussein. I am with Pile Dynamics, Inc. and GRL Engineers, Inc. in the United States. So deep foundations have been used for a very, very long time. Herodotus mentioned the use of driven piles, deep foundations, 2,500 years ago. And now we have structures that are hundreds of years old that are still supported on deep foundations. In today's practice, we use deep foundations to support all types of structures in all kinds of geotechnical conditions to resist all types of load applications. So in a way, one can say that deep foundations are the very foundation of modern civilization because they allow us to support the infrastructure needed for our cities, for our modern living. They consist of driven piles, and there is a very important manual on the design and construction of driven pile foundations that is in 3 volumes written by engineers from our company, GRL Engineers, and can be downloaded from the FHWA government website for free in PDF format. I will leave my email address at the end of the presentation, so please send me an email and I can send you a link how to download this particular 3-volume design manual. So driven piles can be made of wood, concrete, or steel. Wooden piles, timber piles, have been used for thousands of years. In today's practice, they're typically used to support lightly loaded structures or temporary construction, or they use as ground improvement supports. This is a manual that can also be downloaded from the Timber Piling Council for free for the design and construction of timber piles, wood piles. Steel piles are in 2 major varieties, H piles and pipe piles. H piles come in a standard sections of about 20 different standard sections specifically manufactured for the use as deep foundations H piles. Pipe piles come in a variety of sizes in diameter and length. They range in diameter from just a few inches to maybe a few feet to more than a few feet to maybe 3 or 5 meters in diameter. Very large, and also they can be very long when they are used for offshore applications, for oil and gas exploration, and also for wind farms offshore. Concrete piles are typically pre-stressed. They can be regularly reinforced at times, but they can be also pre-stressed. They can be pre-stressed or post-tensioned type concrete piles. And the most recent development in concrete piles is the use of ultra high performance concrete, very, very high strength of more than 25,000 psi, pounds per square inch, F prime sub C strength. While piles are typically uniform and made out of one material, they can also be made of multiple materials in composite and can be highly non-uniform in profile depending on the design requirements. There are hundreds of different hammer models ranging from the very simple to the extremely complex, from the small to large, air, steam, hydraulic, diesel, single acting, double acting. There are literally hundreds of different hammer models available to drive the various pile types and sizes. For a long time, intuitively, people involved in pile driving had realized that there must be a relationship between the energy to drive a pile and how much the pile can carry in load, the load-bearing capacity of the pile, relationship to the energy it took to drive the pile. And Mr. Wellington, in 1888, in the Engineering News magazine, wrote one article that relates the load-bearing capacity of the pile to the weight and drop height of the hammer. This is known as the energy approach or the ENR formula. Many famous people tried to improve on that formula, and we have many hundreds of formulas now available based on that same principle. Some of these formulas are now, they look complicated, but they are not really any more accurate. So it would not be prudent to utilize 19th century approach formulas to today's practice. Not very effective and not recommended for use. So when we drive piles individually, we make a pile group to support maybe a bridge, pier, or a building like this. During pile driving, the pile resistance is dynamic pile driving resistance to penetration. But when we use the pile as a foundation, we need its static load-bearing capacity. In order to evaluate the static load-bearing capacity of a pile, one performs a static load test, where we put load on top of the pile and we load it in compression, and then we plot the applied load versus the corresponding applied pile top applied load and pile top corresponding movement. And we may also put strain gauges along the length of the pile so we can have the strain measurement, the force measurement inside the pile that will allow us to get the load transfer between the pile and the soil, which will allow us to see how much skin friction and its distribution and how much end bearing we have. So this is a static load test, and it is the best way that we can do to evaluate the static load bearing capacity of the pile. However, it has many limitations. It costs a lot of money, and it takes a lot of time to perform the static load test. And in some cases, it could be impossible to do in certain situations. Also, there is an aspect of safety when we perform these static load tests. So although it's a good thing to perform for a load test, it has many limitations in real practice. So the challenge that we have is how do we get from the pile driving resistance during installation to the actual static load bearing capacity in service. Many very smart people for 500 years have thought about the dynamics of bodies in motion. They come up with a wave equation, stress wave propagation, and elastic theories that apply to pile driving. A very smart engineer called Mr. Edward Smith in the 1940s in Texas in the United States, realizing that the dynamics of pile driving are best represented by theories of stress wave propagation, elastic, one-dimensional stress wave propagations in the pile, and he wrote a computer program that utilizes the wave equation, stress waves in the pile to solve the dynamics of pile driving. He wrote a computer program called the Wave Equation Analysis of Pile Driving. This program that Mr. Smith wrote in 1948 is often cited as the first program in civil engineering. The first computer program written in civil engineering is this Mr. Smith program to follow the stress wave in the pile, the dynamics of pile driving. In today's practice, the most widely used program, maybe worldwide, for the dynamic analysis of pile driving is called GRL-WEAP, as commercialized by Pile Dynamics, available from Pile Dynamics. So it's a predictive computer simulation program that uses numerical methods to include pile drivability. So we can assess the driving of the pile by simulation beforehand that provides information relating the pile driving resistance and blow count, blows per meter, to ultimate static load bearing capacity. So this can be used by the pile driving inspector by utilizing a unit called the saximeter on site to follow and to automatically calculate the stroke of the diesel hammer, for example, and also to count the blow count every quarter meter of penetration to generate a completely automated pile driving installation log of the pile driving that can be used as a quality control and assurance to drive every pile to the required resistance. However, being a simulation program, it depends on a variety of assumptions to generate the model that is needed to perform the numerical analysis using wave propagation theories in the computer by simulation. But some of these assumptions are very difficult to assume and to obtain and accurately, such as the hammer performance, efficiency, the cushions of the material inside the hammer, and the soil pile-soil interaction, how much skin friction resistance, how much in-bearing resistance, and the elasticity of the soil to pile driving. So all of these assumptions are sources of error in the simulation type analysis of pile driving. So instead of assumptions, what if we think about measurements? So if we go out on the job site and we measure what we need to know and analyze these measurements using stress wave propagation methods, that will allow us to obtain information regarding the performance of the hammer, the pile driving stresses, pile integrity assessment, and pile static load bearing capacity. So this idea of application of stress wave theory by measurements came about in the 20th century, starting in 1938, where we had the first strain measurements done in Australia, and then in the United States, in Cleveland, the first pile capacity computer equipment, and the Dr. Rausch's PhD dissertation on the CAPWAP method. The history of the application of stress wave theory to piles had been summarized in this paper published by the American Society of Civil Engineers. So between the period of 1964 and 1976 at Case Western Reserve University in Cleveland, Ohio, USA, a research program was undertaken, the goal of which was to come up with an accurate, reliable, cost-effective means to determine static load-bearing capacity from dynamic measurements during pile driving. That research was sponsored by the United States Federal Highway Administration, the Ohio Department of Transportation, as well as many states such as Florida, Georgia, Minnesota, New York, and others. That research was headed by Professor George Goebel and Dr. Frank Rauschi and Gordon Likens. So they invented, during that research, they invented the equipment, the sensors, and the computer that were needed to take these dynamic measurements during pile driving. They issued their final report in 1975 that included the outline of the schematic of the equipment needed for instrumentation and also for the processing of the data, as well as the science, the formulas needed to calculate the static pile load bearing capacity from the dynamic measurements during pile driving, as well as correlations. They have about 60 or 70 different correlations comparing the prediction of static load bearing capacity from dynamic measurements to the actual full-scale static load test, and the correlation showed excellent comparison. So the researchers felt very confident that yes, we can perform dynamic measurements during pile driving. We can calculate static load bearing capacity values from these measurements that compares excellent with the actual full-scale static load test. So these are the measurements that were taken during the research, and this is a big computer that was used to analyze these measurements. So one can call this equipment the first pile driving analyzer. It is the first computer used to analyze pile driving data. Nowadays, the instrumentation is very, very simple. It consists of two instruments, like 10 centimeters long each, only 3 inches long, very small, that are attached to the pile. They consist of a strain gauge and an accelerometer. And the big computer that was used before now had been reduced in size to a tablet size, as you see this engineer holding it on a job site. The gauges, the sensors used to perform dynamic pile testing can easily be attached. They are reusable, can also easily be attached and taken off all types of pile types, as well as gas in situ foundations such as bored piles and drill shafts, and gas in place piles. So let's start from the beginning. This is a static load test. We need all of this dead weight to perform a static load test because we want to load the pile statically. That's how we perform a static load test. What if we were to think a little outside the box, a little differently? If I take a small portion of this dead weight and put it in a guide, lift it up high enough and drop it in such a way that that will produce the same load on the pile as all of this dead weight. That is basically the difference between a static load test and a dynamic load test. I don't have to do any of this. This is being done on the job site with the pile driving hammer. So during the pounding of the pile, during the installation of the pile with the hammer blows, the pile is being dynamically loaded. So all we have to do now is to put instruments on the pile and perform dynamic load testing during the pile driving process. So the impacts of the hammer are the loading process needed to perform dynamic load testing during initial driving. This had been standardized by ASTM standard D4945. Testing can be done with the testing engineer on the job site in real time, or it can also be performed in real time using site link technology by remote testing. So the equipment can be on the job site, sending the data in real time to the engineer in the office, following the project, following the driving of the pile, and doing the testing, performing the testing remotely in real time. So dynamic pile testing is a measurement of pile strain, therefore force, and acceleration, therefore movement. So dynamic pile testing is a measurement of pile force and movement under the impact of the hammer, and the analysis of these measurements using elastic stress wave propagation theories. The measurements are done with a pile driving analyzer, and the analysis is done by a program called CAPWAP, Case Pile Wave Analysis Program. When the hammer hits the top of the pile, it generates a stress wave. When the stress wave reaches a gauge location, 1 meter below the pile top, the strain and the movement of the pile see a very sudden jump in value. Then the stress wave leaves the gauge location, travels down the pile length, reflects from the pile bottom, and then the gauges sense it again. So therefore, this is one data from one hammer blow indicating impact at the pile top and reflection from the pile bottom. Of course, the wave goes up and down many, many times during the one hammer blow. It takes about 50 or 100 milliseconds for the whole cycle to go back and forth. One travel cycle, one round trip down and up is about 5 to 10, maybe 15 milliseconds, very short time. So the measurements for one cycle, impact and reflection, one time reflection from the pile toe, we measure it in time domain. Then we can change it to length domain by knowing the constant stress wave speed of the pile material. So although we're taking measurements of the time domain, we do the analysis and the evaluation in the distance domain or length domain of the pile. There are two fundamental principles that we have to keep in mind when we do dynamic pile testing, which is 2L over C. L is a pile length, and C is celerity or stress wave speed value. The other value is called Z, which is a pile impedance that gives us a relationship between the two independent measurements of force and velocity. So we need the value 2L over C because that is how we track the movement of the stress wave down the pile and back up. It will give us the timing of the wave reflections. And the impedance value Z will give us a relationship between the measurements, the independently measured force and velocity in the pile, because force and velocity are proportional, are directly related to the impedance of the pile. The impedance of the pile, Z, is a quantity EA over C, elastic modulus times area divided by the stress wave speed. So it is a constant for a specific pile type and size. So if we know the impedance of the pile by knowing its elastic modulus, its area, constants, and wave speed, a constant, we multiply that by the measured velocity, then we can relate that to the measured force. From these measurements of force and velocity at the pile top, then we can calculate the wave going down the pile and the wave going up the pile. So now we have the waves in the pile going down from impact of the hammer and wave up as reflected waves under each and every hammer blow. Since we're taking the measurements during pile driving under each and every hammer blow, now we have a complete full record of the installation and therefore the testing of this pile in its entirety. Every blow has a value. Now we can then group all of these different blows. We can average them per 25 centimeters of pile installation or per meter or per foot or per inch. And then we can group them as such and we can plot them as a function of pile penetration depth. So the y-axis is pile penetration depth and the different quantities versus penetration depth are shown. For example, if we look on the data on the right-hand side, the blue line is the static load bearing capacity of the pile versus penetration depth, and we see the scale there. And then the red line, the corresponding red line, is the blow count versus depth of this pile, in this case shown in blows per foot. It can also be shown in blows per meter or blows per 25 centimeters. So this gives us a full record of the pile installation of this pile, data of capacity and blow count versus penetration depth. This data can then be used to evaluate the hammer performance, the pile performance, and the soil performance. So the hammer performance. The hammer has a potential energy, which is the rated energy of the hammer, which is a weight times height. Weight times drop height is the maximum energy of the hammer. Then the hammer falls, it drops, compresses the cushion inside the hammer, accelerates the helmet on top of the pile, compresses the plywood cushion if we're driving concrete piles, for example, and finally reaches the top of the pile. We call that maximum transferred energy. The ratio of maximum transferred energy to the pile as a percentage of the maximum potential energy of this hammer varies widely. So the best measure of hammer performance is to measure how much energy the pile actually receives with the pile driving analyzer, with the PDA. We measure the amount of energy under each and every hammer blow. Then we compare that to the potential energy of the hammer or the rated energy of this hammer. This range can vary widely, somewhere between 10% to 80%. It could be anything in between. So why does it vary so much? That it varies so much because depending on the mechanical condition of the hammer, the state of maintenance of the hammer, as well as the condition of the cushions inside the hammer, and the condition of the cushion on top of the concrete pile. Because of all of these reasons, the hammer varies widely, how much it transfers. Of course, this is very important when we're using this hammer energy, when we're driving piles according to a blow count criteria to make sure that the hammer performance is up to the level that is required to provide the capacity of the pile based on hammer driving blow counts. So that's the performance of the hammer that is established under each and every hammer blow. Now, pile performance. Under the impact of each hammer blow, the pile undergoes a very complex state of stresses that includes compression, tension, torsion, and bending. The data that is obtained, the measurements that are obtained under each hammer blow will allow us to evaluate the stresses on the pile and the integrity of the pile, structural integrity of the pile. So from the measurements themselves, we can use them to control the stress in the pile because we're measuring force, therefore we know the stress in the pile in compression under the impact of the hammer. So that will allow us then to evaluate the stress level in the pile and therefore try to reduce the risk of damaging the top of the pile under the impact of the hammer, under the initial impact of the hammer. Since it's a dynamic measurement over time and the stress wave on the pile, we can calculate from the measured values, from the measured stress value at the top of the pile, we can calculate the stress value anywhere along the length of the pile, any location X, including X equals L, which is the pile length. The pile tip stress is a very special location because when we drive piles to a very hard layer, the stress at the bottom of the pile can potentially be twice that at the top of the pile. We can have 2 times stress at the bottom of the pile in compression as that on top of the pile. That is because the stress at the top of the pile, the compression stress at the top of the pile, is coming from the hammer impact. That compression stress wave reaches the bottom of the pile. If we have a very hard end-bearing layer, it will activate an equal and opposite reaction, end-bearing reaction, both in compression. So the initial compression wave interacts and adds up to the reflected compression wave, both located at the bottom of the pile. That is why we could potentially have twice as much stress at the bottom of the pile than that on the top of the pile. We calculate that, compression force at the bottom, compression stress at the bottom. Here's a project where they drove these piles to a very hard layer, very large, high end bearing resistance. We see the top of the piles, there's no damage, but when we extract some of these piles, we see that there's damage at the pile bottom because of this doubling effect of stresses at the bottom of the pile because of very high end bearing resistance and high initial impact compression stress. Should we be driving a concrete pile, and then when the compression stress from the hammer comes down, traveling the length of the pile, if we do not have any resistance or very little resistance, low resistance, then that compression wave, when reaching the pile bottom, it will pull down on the pile, putting the pile in tension. And if we have too much tension in the pile, we may cause a crack in a concrete pile. This is why concrete piles crack in tension during easy driving from the compression wave initially reaching the bottom of the pile and reflecting up as a tension wave, elongating the pile. And if that is too high, then the pile will be cracked. That will also allow us to draw a tension envelope in the pile. We know the amount of tension along the length of the pile, which would be very important, for example, to know at special locations, such as the location of a spliced pile. If a splice in a concrete pile, a splice in a concrete pile will put a weak link in the pile with limited tensile strength. So we will need to know not only what is the maximum tension stress in the pile, but additionally, by utilizing the measured data, we can draw the tension envelope in the pile, and then we know how much at the exact location of the splice, what is that stress level is, so we do not break the pile or the splice in the pile. Should there be a break in the pile, should there be a crack in the pile, that crack will send back a tension reflection stress wave that reaches the top of the pile. So by using like pulse echo type calculations, we're able to calculate the location of that wave reflection, origination depth, which means location of the crack, location of damage, and also the amount of damage, depending on how much energy gets reflected. So we are able to calculate the location of damage and amount of damage, if it's just a small crack or complete break. And this is data showing early reflections indicating damage in this extracted concrete pile, as well as damage at the bottom of this steel pipe pile from the measured data. And this is also data from a concrete pile showing damage at the very bottom of the pile. This is a very large pile, 24-inch in size. So we talked about hammer performance, we talked about pile performance. Next, we will talk about pile-soil interaction performance, or soil resistance performance, and static load-bearing capacity. So when the hammer hits the top of the pile, it generates a stress wave, stress times area is force. So the hammer forces the pile down into the ground. It moves the pile, displaces the pile. When the pile displaces against the soil activates soil resistance in skin friction and end bearing. Both the impact of the hammer and the reflected wave produce data in the measurements. So the measured data, therefore, incorporates the wave going down the pile, wave down from the hammer, and the wave going up the pile from the soil resistance in the PDA measurements based on these measurements at the pile top of force and motion, strain gauge and accelerometer. So when the hammer hits the top of the pile, we have a quick increase in force and velocity of the pile as measured in the data. Then the stress wave leaves the location and arrives at the pile bottom, and it gets reflected, depending on the end condition. If we have a free end or no resistance, then the reflection will be zero force and very high velocity. So the pile will move more down because there's no end bearing. If we have end bearing resistance, then the reflection will be the opposite. When we have no resistance, the reflection from the pile bottom on the right-hand side of the plot consists of zero force because we have no resistance, and very high velocity also because we have no resistance. But if we have a lot of end-bearing resistance, then the force is high, solid line, and the velocity is zero at the pile bottom. So that is the difference between the end-bearing and no end-bearing resistance in the measured data at the pile top. If we have a situation where we may have a displacement type pile, a high displacement pile, and it is rebounding, we have a lot of elastic rebound, that expresses its way in the measured data as we see. So the top plot shows regular pile-soil interaction, and correspondingly in the bottom plot, it shows similarly, but with a high elastic rebound. The pile is high elastic, so we need a lot more blow count. When we have elastic rebound, we need a lot more blow count to achieve the same static load-bearing capacity. So if we have 1,000 kips capacity, if we have normal pile driving, we need 48 blows per foot. And if we have high elastic rebound, to obtain 1,000 kips, we will need 350 blows per foot. So the rebound effect is expressed in the measurements of the data at the pile toe. So now, again, if the hammer hits a pile top, the stress wave goes down. If we have now skin friction resistance, skin friction will tend to increase the force on the pile and reduce the velocity. So as the wave goes down the pile length, if we have skin friction resistance, then the solid line, which is the force, will increase, and the velocity, which is the dotted line, will decrease along the pile length until we get to the pile bottom. So therefore, a pile with skin friction resistance will indicate in the pile measured data, pile top measured data, a separation between the force and the velocity between the pile top and the pile bottom. So this data here on the pile top shows end of initial driving data, showing a little bit of skin friction by the separation in the measured data of force and velocity between the pile top and the pile bottom. In this case, we have 200 kips of ultimate pile capacity, 150 in skin friction, and 50 kips in end bearing. The blow count is 32 blows per foot at end of initial driving. We gave this pile some time to set up, so we did a restrike test. Now, as we can see, the force and velocity have more separation, so have more skin friction. So the total pile capacity and restrike, due to the time effect of consolidation of setup, we have 450 kips, 400 of which in skin friction and 50 kips in end bearing. Now the blow count had also increased to 80 blows per foot. So this is how we see the effect of the setup on the pile capacity versus time, and the calculation of capacity, increased blow count, and increased skin friction resistance as demonstrated in the measured data. This is the opposite effect. This is where we may have a situation where we have relaxation. Relaxation typically happens at the tip of the pile in end bearing. So this is data from end of initial drive, 130 blows per foot, 500 kips capacity, 150 kips in skin friction, and 350 kips in end bearing at the end of driving. If we give the pile time and we tested in restrike, the capacity had decreased from 500 to 300 kips. The blow count decreased from 130 blows per foot to 68 blows per foot, and the decrease of capacity was in end bearing. And there we see a huge velocity increase in end bearing resistance as opposed to the end of initial drive. So initial drive has high resistance. That's why the velocity was low at the tip of the pile. And in the restrike, because of relaxation effect, the velocity of the pile now is much higher. The pile is moving more in the end bearing due to relaxation effect. So in any event, this is how relaxation expresses its effect in the measured data between end of initial drive and restrike testing. So these resistances that go up the pile generate a wave up the pile. So we add the wave down and the wave up, and we can calculate, we can quantify the amount of total resistance of the pile, and also the location of that resistance in skin friction along the length of the pile and in end bearing. We can quantify it and qualify it as well with the measured data. We can quantify it with this formula that we can calculate the static load bearing capacity from the measured pile top force and velocity record, wave down and wave up. This is a paper that proposed that method called the CASE method, and that has been published by the American Society of Civil Engineers as one of the top 100 most important papers in geotechnical engineering. Then from the measured total resistance, we can calculate a static load bearing capacity by introducing a dynamic damping factor of the soil, depending on the soil type. We plug it in the formula that takes into account the measured wave down and wave up from the data and calculates a static load bearing capacity. We can further, that is done in real time on the job site by the PDA, by the pile driving analyzer for each and every blow. We assume the waves, we assume the damping factor depending on the soil type. We can then take the same measurements and apply the analysis of case pile wave analysis program, CAPWAP, that uses signal matching techniques to resolve the measured data into skin friction and end bearing by taking into account the actual profile of the pile. If the pile is non-uniform, we can model exactly the pile profile in area and maybe material change as well along pile length. Then we can concentrate on the evaluation of pile-soil interaction by utilizing these models of static and dynamic components of the soil resistance, as well as take into account any dynamic radiation damping into 3D into the soil. So we use this CAPWAP program by simulation of the measurements going down, by utilizing the measured wave going down and simulating a wave up that we compare to the measured wave up by signal matching process interactively between the engineer and the computer to come up with the best fit, best match of the data. It can also be done, this process can also be done completely automatically by the pile driving analyzer on the job site as well, the signal matching by ICAP. So the result of this CAPWAP analysis then is the separation of skin friction, static load bearing capacity and skin friction, and end bearing, and the distribution of skin friction along the pile length, which will then allow us to simulate the static load test result. So now we have a simulated static load test result from the measurements of the PDA and the CAPWAP. We can simulate pile top load versus movement. So how good is that? How does that compare to actual full-scale static load test? There have been many studies in the literature independently comparing the calculated static load bearing capacity of dynamic measurements to actual full-scale static load test by many researchers and many practitioners worldwide over the last 50 years. If we have good quality data, good competent analyses, one can expect to have a good correlation between the simulated static load test result and an actual full-scale static load test, as we see in this case. But additionally to the quality of data and analyses, one will have to use some considerations of engineering principles to have a best result of the dynamic pile load test data. This is a paper by the American Society of Civil Engineers that utilizes the use of superposition to evaluate pile capacity from dynamic measurements. So the pile was driven to end bearing resistance to a very high blow count. This is the data from the end bearing, from the end of initial drive, showing 200 kips in skin friction, about 900 kips in end bearing, and a total of about 1,100 kips. Performing static load test, the static load test showed 1,600 kips, much higher than the end of initial driving. That is because of setup. So we did restrike test, and that restrike test showed also low capacity. It showed 700 kips in skin friction, 200 kips in end bearing. So now, what if we were to use superposition? If we take the end bearing from the end of initial drive and the skin friction from restrike, add them together, we come up with that 1,625 kips. That compares very well with the actual static load test, 1,630 kips. So using superposition, when we have cases where the hammer energy is not sufficient to fully mobilize all of the capacity in restrike because we have so much skin friction, added to the already very high end bearing from end of initial drive. So this is one case that shows the use of engineering considerations in evaluating the dynamic resistance during initial drive, the static load bearing capacity during initial drive, and in restrike, and a holistic approach to come up with the best result of the test that compares very favorably well with an actual full-scale static load test. And this is a simulation on this case, from this case, of the full range of static load test and simulated by CAPWAP utilizing this superposition procedure. So this dynamic pile testing is typically applied on a project by way of a test pile driving program where the engineer may choose a number of piles, test piles to drive, and to test them with the PDA, analyze them with the CAPWAP program in order to establish production pile length and production pile driving criteria, as well as to check the engineer's design assumptions of the foundation, and also to check the contractor's equipment, means, and methods. That is a standard conventional way of applying dynamic pile testing on a pile driving project. It has been done this way for about 50 years. Alternatively, the modern practice, for example, in the state of Florida, every single pile is tested. So we have 100% dynamic pile testing, whether we use the test pile program or not use test pile program. Every pile, test pile and production pile, are tested with the pile driving analyzer. They have found that this optimizes construction efficiency and economy. It actually makes the project less expensive than running an independent test pile driving program, and also it increases the engineer's reliability. So if the engineer knows that every pile is tested, verified for integrity and capacity, then the design can utilize a much lower factor of safety that makes the foundation much more efficient and economical. So that was testing of driven piles. Now we can apply the same dynamic load testing to also drill shafts, board piles, and auger cast in place pile. So it's in addition to applying dynamic pile testing to driven piles with a hammer, we can also apply it to cast in place, cast in situ, deep foundations, board piles, and drill shafts. There is a manual also of drill shafts that you can download from the same source I mentioned earlier, as well as that for auger cast piles. There's also a design and construction manual you can also download. So we know that we are familiar with low strain testing. So with a small handheld hammer, we send down a stress wave, we wait for reflections, we use that for integrity. This will tell us something about the integrity of the shaft, but nothing about the load-bearing capacity. To evaluate load-bearing capacity, we need a bigger hammer. We need a big enough hammer to move the shaft. We have to perform a high-strain dynamic load test to move the pile against the soil to activate resistance to calculate load-bearing capacity. Well, how big should the hammer be? We have to bring in a drop hammer and impact the top of the drill shaft. How big should the hammer be? This is a paper from a stress wave conference that goes into the details of how big should the hammer be. The summary of which is that the hammer weight is about 1% to 2%, let's say 2% of the load you're trying to test to. So if you know we're testing to 1,000 tons static capacity test, we need 20-ton hammer. Additionally, we can also apply thermal integrity profiling by putting these thermal wires along the length of the reinforcing cage and the drill shaft, board pile, in order to measure the temperature and then evaluate the shape of the pile, because the shape of the pile will be variable. We will need this information in order to model the pile shape in our dynamic load testing data. This method of integrity profiling of the cast in place drill shaft has won so many awards. It is the most innovative introduction of technology in deep foundations for the last many years. So it relies on the measurement of the temperature by utilizing the heat created during the curing of the concrete due to the cement chemical reaction inside the drill shaft during curing. So during the first 1 day or 2 days of curing of the concrete inside the shaft, it generates heat that we measure the temperature using these wires, and we get a profile of the shaft. We get a profile of the concrete from these measurements of temperature using thermal integrity profiling. So we can get the shape of the drill shaft in the ground, then we can then plug that into the data, into the dynamic measurement data. I just want to mention that this type of thermal integrity profiling has also been used on berths and diaphragm walls for integrity assessment. In any event, we get the drop hammer, we put it on top of the shaft, we have already the profile from thermal integrity profiling, we can plug into the model, and then we can calculate using signal matching like we did before with the CAPWAP program and come up with a static load test simulation. So we can do the simulation of the soil resistance because now we know the profile of the shaft from the thermal integrity profiling. So this is putting together the integrity testing result with the load-bearing capacity result, thermal integrity profiling, and PDA CAPWAP results for best analysis of the data. Dynamic testing can also be used for other applications, such as the calibration of the SPT hammer energy. So ASTM requires the calibration of the hammer energy because we rely on the end values of the SPT hammer to design the foundation with. But the end value, the number of blows, is also dependent on the efficiency of the SPT hammer. So the hammers are supposed to be calibrated, for which this dynamic measurements can be used to calibrate SPT hammers. Dynamic testing can also be used to test micro piles with the use of a small drop hammer, as well as very huge piles for offshore applications by the use of pile driving hammer. Dynamic testing can also be used to test helical piles for load-bearing capacity assessment by using a small drop hammer performing dynamic load testing. as well as in the United States, what is called a Becker drill testing that is used to evaluate characterize the soil, the site for liquefaction, and therefore seismic design considerations. This is a very unique application of dynamic testing by testing this very large 3-meter diameter, 100-meter long pipe driven horizontally, laying down under a roadway and railroad track to form a tunnel. So they drove this pile using a hydraulic hammer, laying down horizontally to use as a tunnel, and dynamic pile testing was used to control the driving so that they do not have any effect on the roadway and on the railroad track above it. We're familiar with static load testing. We're familiar with bidirectional load testing. So when we evaluate the data for these tests, when we perform the test and we put strain gauges along the drill shaft to evaluate the load bearing capacity and to evaluate the load transfer or using the strain gauge measurements, we need the profile of the drill shaft. We need the area versus depth versus length of the drill shaft in order to evaluate the load transfer. We have to calculate force from measured strain. And to calculate force from measured strain, we have to know the area. So the thermal integrity profiling will allow us to get a profile of the shaft, the area profile, so we can more rationally and accurately analyze and evaluate the measurements of the strain to calculate force, therefore to calculate the skin friction in the pile, but from the static load test, whether it's a bidirectional static load test or a conventional top-down static load test. Every shaft should be fitted with these thermal wires from thermal integrity profiling. That is the only way we can get a good profile of the shaft in place, and the only way we can have a rational analysis of the measured strain to come up with force in the pile and therefore skin friction between pile-soil interaction. So we need that profile. So whether it's a dynamic load test, a static load test, a conventional static load test, or a bidirectional static load test, they should all, these gas-in-place piles, gas-in-place shafts should also be fitted with thermal integrity profile wires in order to give us a profile of the shaft we need for the proper analysis of the load test data. So all of these methods I mentioned to you today are widely available in standards, in codes, in specifications, in conference proceedings, in reference books, in textbooks. So there is no shortage. There's a lot of data available and information of correlations that describe the methodologies, the principles of the methods, their limitations, and their capabilities. The previous presentations by Mr. George Baim and Mr. Garner Likens had gone over other aspects of testing of deep foundations having to do with CSL testing and thermal integrity profile testing for integrity assessments. I wanted today to concentrate on the assessment of load-bearing capacity by dynamic testing. These testing methods, as I described to you today with the PDA and CAPWAP, are used worldwide. We estimate them to be used on more than 5,000 projects each year worldwide. So there's a lot of experience gained every day using these methods of evaluating deep foundations. So with that, I thank you for your time. I thank you on my behalf and my company's behalf, GRL Pile Dynamics. This is my email address, very easy to remember, mhussein@pile.com. If you have any questions, please give me an email, send me an email. I'll be more than happy to engage and reply. If you would like links to the manuals I mentioned to you, and I highly recommend that you obtain these manuals. They are very extensive and probably the state of the art in the literature for the design and construction of driven piles, board piles, drill shafts, and cast-in-place piles. With that, I think we have a few minutes left for questions. I'll try to answer them. Otherwise, please keep the communication and send me an email as the questions may come to mind. I give it back to you now in case you would like to field any questions anybody may have who may be present here today.
Thank you for the presentation, Dr. It was incredible. We have some questions here, and I will read some. If you wanna back, like for the other page, you can see the questions too, but I will read.
Yeah, please read it. I cannot see the question on my screen.
Okay. Sergio Paraíso, he said, regarding the application of the beta values to assess the integrity of cast and place piles in general. I have a position that should not be used as, so what do you think about this?
The use of dynamic testing on composite piles, is that the question?
In general, yeah.
Yeah, so
Okay.
for composite piles, you take the measurements under the impact of the drop hammer, and then to analyze the measurements, you have to use CAPWAP program signal matching, where you are able to fully model the non-uniform composite pile section. So you can put the accurate representation of the pile in the model of the CAPWAP analysis, then apply the measured data that will allow you to have an accurate assessment of the soil resistance effect, because you're able to represent the pile model accurately, if composite pile or non-uniform pile.
Other question of Sergio is, in a case of steel piles and precast concrete piles, what is the best way to assess structural damage? Better value or interpret the thrust of wave up?
I think you need an excellent question. The damage will cause a wave reflection. That wave reflection is best expressed in the wave up. So since you have the measurement of force and velocity, you can evaluate force and velocity, but also since you have the same measurements of these blows showing the wave down and the wave up. So you can use that to assess the location and to analyze the amount of damage that may be at that location by using wave down and wave up data.
Now a question for Clayton Delacote. Could you explain the limitations of using DLT to estimate the load displacement behind of pile under service strategic loads?
So the limitation of the dynamic load testing, there's really, in the case of drill shaft and board piles, the only limitation I see is that you have to bring a hammer, because during pile driving, the hammer is present naturally to drive the piles. So we use the impacts of the hammer to perform dynamic load testing. But in the case of drill shaft, you have to bring in hammer that you do not need to construct the pile, the shaft, the board pile or drill shaft. You have to bring in a hammer. So in areas where they use a lot of drill shafts or cast-in-place piles, they typically have drop hammers that they use to perform dynamic load testing. So it's convenient if the hammer is available. And with that, I thank you for your time. With any more questions, please send me an email. I'll be more than happy to engage in a discussion and to always reply.
Thank you, and good afternoon, everybody. Remember, the presentation will be saved, so you can watch whatever you want and be back to watch us. So thank you so much for your time. And yeah.
Thank you.
Bye-bye.
And goodbye.
Goodbye.